In previous sessions, we've looked at how to go about solving systems of equations with two variables. In this lesson, we're going to look at how to do so with three variables. Our first goal is to reduce the number of equations or the number of variables from 3 to 2 by eliminating one variable in various pairs of equations. So you're going to pick one equation and one variable and use that equation with each of the other two equations to eliminate the variable of interest. It can be x, y, or z. By adding together multiples of our pairs of equations, we end up with two new equations that have two equations and two unknowns. This can then be solved using either substitution or elimination, and it will result in us now knowing one of the three unknowns, or one three-dimensional variable on which the three planes meet. This can then be plugged back into one of our two second phase equations to find a second variable. This can then be back substituted into one of our three first phase equations to find our third variable. So if we start out with the three equations, equation A, 2x plus 3y plus 7z equals 13. Equation B, 3x plus 2y minus 5z equals negative 22. And equation C, 5x plus 7y minus 3z equals negative 28. We want to pair these up. We're going to be working with A and B and A and C. And since our z variable has a positive 7, a negative 5, and a negative 3, by multiplying through by positive numbers, we can end up getting opposite coefficients. So for equation pair AB, we multiply the top equation by 5, the bottom equation by 7, and we get a new equation D, 31x plus 29y equals negative 89. Equations A and C. Again, we're going to be eliminating z. To get these to be opposites, we multiply the top equation by 3, the bottom equation by 7. And then when we add, the z's cancel out again. Get 41x plus 58y equals negative 157. Then we take equations D and E, and when we double D and multiply through by negative 1 on D, or multiply through by negative 2 in the first place, we end up with our y's being opposite. So we have negative 62x minus 58y equals 178, plus 41x plus 58y equals negative 157. Negative 21x equals 21, or x equals negative 1. We then substitute our negative 1 in for x. 41 has negative 1 plus 58y equals negative 157, or 58y equals negative 116, or y equals negative 2. We can then take the x that we know, the y that we know, plug it into one of our three equations above, a, b, or c. In this case, I chose C. Get -5 plus -14 minus 3z equals -28. -3z equals -9, or z equals 3. So our three independent planes intersect at a common point, -1, -2, 3. So again, to solve three equations and three unknowns, and it is possible that two of the planes can be overlapping or parallel, but assuming that they are dependent and consistent, then we have to take our three equations, three unknowns, reduce it to two equations and two unknowns by using pairs of our equations to reduce the whole thing by one variable. Then once we have our two equations, two unknowns, we work through those to get down to one equation with one unknown, which can then give us one equation with one known, and back substitute our way back up. Okay, have a good one.